Forget the gas giants. Forget the distant exoplanets with fancy names. The most extreme planet you're going to meet lives right next to the sun, and you already know its name, Mercury. In this video, we're going to tear apart that small gray rock image you've had since school and show you a world that pushes speed, gravity, temperature, and raw physics to the edge. By the time we're done, Mercury won't feel like the planet you skip on the way to Venus and Mars. It'll feel like the prototype for the most brutal, star-hugging world in the universe, and the place where our ideas about what a rocky planet can be finally break. But before we continue, please subscribe to the channel to give your support. Let's continue. Start with its size. Mercury is only about 4,880 kilometers across, around 3,030 miles. That's just a bit wider than the continental United States. If you laid it on a map, it would basically cover coast to coast, and that's it. So your brain says, okay, tiny planet, probably light, probably not that serious. But then you look at its density, how much mass is squeezed into that volume, and it hits almost the same average density as Earth, about 5.4 grams per cubic centimeter. Earth is about 5.5. That should not happen for something so small. Here's why that's strange. Smaller rocky planets normally end up less dense. There is less pressure inside them, so the material is not as compressed. But Mercury refuses to follow that rule. Its density is telling you very clearly, I'm packed with heavy elements, mostly metals. Instead of being a normal rock and metal mix like Earth, Mercury is mostly core. An iron-nickel core that likely takes up around 85% of the planet's radius. Earth's core takes up about half the radius. So when people say Mercury is a core with a little bit of planet around it, that's not a joke. It's a straightforward description. That alone raises a hard question. What had to happen in the early solar system to build something like this? One main idea says early Mercury used to be bigger, more Earth-like. Then a huge impact stripped off most of the lighter rocky layers and left the metal-rich center. Another idea says the young sun blasted away lighter material from the inner disk of gas and dust, so only the heavy stuff survived that close in. Whichever way you pick, the message is the same. Mercury's basic existence means something extreme happened very early on. It is not a calm, default outcome. Now add motion. Mercury does not just sit close to the sun, it races around it. Its orbital speed is about 47 kilometers per second, around 170,000 kilometers per hour, around 105,000 miles per hour. Use Earth as a comparison. Earth moves at about 30 kilometers per second around the sun, already incredibly fast. Mercury is going more than half again as fast. If you could move along with Mercury at that speed near Earth, you could go all the way around the equator in about 34 minutes. A passenger jet would take more than a day to do that. Mercury does it in less than the time it takes you to watch a movie. That speed is not a random number. The sun's gravity is much stronger where Mercury orbits. So to stay in orbit and not fall in, the planet must move very fast, sideways. If it moved slower, it would spiral toward the sun. If it somehow moved faster, it would climb outward. So that 47 kilometers per second is not random. It's the exact speed that keeps this tiny, dense planet just barely hanging on to a stable path that close in. So then the next question is simple. What kind of gravity field forces a planet to move that fast just to stay alive in orbit? Solar gravity at Mercury's distance is on another level compared to what we feel at Earth's distance. Out here at Earth, the sun's pull on us sets our orbital speed at about 30 kilometers per second. Closer in, at Mercury, that same sun is pulling about 6 to 7 times harder than it does at our orbit. That stronger pull is what drives Mercury to that extreme 47 kilometers per second. And it also explains why going down the sun's gravity well is such a brutal challenge for spacecraft. If you send a probe toward Mercury, you're not just steering inward, you're dropping into a much deeper gravity field. So your spacecraft automatically gains speed. If you don't slow it down aggressively, it just whips past Mercury and back out. This is the part that breaks a lot of people's expectations about space travel. Going to Mercury actually costs more fuel than going out to Jupiter, even though Jupiter is much farther away in kilometers. To reach Jupiter, you can lean on the sun's gravity to help accelerate you outward and use gravity assist to shape the path. To reach Mercury, you have to cancel a big chunk of the speed you already have from orbiting the sun with Earth, then keep dumping speed as the sun drags you faster and faster. Missions like Messenger and Baby Colombo have to do multiple flybys of Earth, Venus, and Mercury itself just to bleed off enough energy to be captured. Mercury is not just a small target, it sits in a very deep, very steep part of the sun's gravity field. But if the gravity is so strong and the orbit so tight, does that orbit actually stay fixed, or does something more subtle happen over time? This is where Mercury starts to stress test the laws of gravity themselves. Its orbit is not a perfect closed loop in space. The closest point to the sun, the perihelion, slowly rotates around the sun over time. This slow twist is called precession. You can picture it like the whole oval orbit turning century after century. Most of that precession can be explained by Newton's law of gravity and the pull from the other planets, especially massive ones like Jupiter. When astronomers did the detailed calculations, though, there was a stubborn leftover, about 43 arcseconds per century. That's a tiny angle, but it is real and measurable. For decades, that mismatch was a serious problem because Newton's equations worked incredibly well almost everywhere else. Mercury was the exception that would not go away. Then Einstein came in with general relativity, which says gravity is not just a force, it is the curvature of space-time itself. Near a very massive object like the sun, space-time is curved more strongly, especially close in. When you apply Einstein's equations to Mercury's orbit, that extra 43 arcseconds per century appears naturally. No extra tweaks, no hidden planet, just the effect of curved spacetime near the sun. Every time Mercury goes around, its path feels that curvature, and the perihelion shifts a little. This means Mercury is not just another planet in a diagram, it is a continuous, real-world test of general relativity. Radar ranging and spacecraft tracking let us measure its position and motion extremely precisely, and so far, every one of those measurements lines up with Einstein's predictions. If there were a serious flaw in our current theory of gravity at these scales, Mercury would be one of the first places it would show up. So when you look at this small, hot world, you're not just seeing a planet, you're looking at a live experiment that runs every 88 days, putting one of the most important theories in physics under pressure. If relativity and gravity together are twisting the orbit like that, what does that actually do to Mercury's seasons and surface conditions? Because Mercury's orbit is stretched, the difference between being at perihelion and aphelion is huge. At perihelion, around 46 million kilometers from the sun, the energy hitting Mercury's dayside is drastically higher than at aphelion, around 70 million kilometers out. The sunlight intensity scales very strongly with distance, so this change is not a minor seasonal shift. It is a harsh spike in radiation when Mercury swings in close. If Mercury had a thick atmosphere like Earth, that air could move heat around, spread it from day to night, from equator toward the poles, and smooth out those differences. But Mercury does not have that. It only has a thin exosphere, a near vacuum. So instead of gentle, planet-wide seasons, Mercury gets brutal local extremes. When a region is facing the sun near perihelion, the ground is hit with very intense radiation for a long time. The surface heats up toward about 430 degrees Celsius, around 800 degrees Fahrenheit. That is hot enough to soften some metals. When that same region rotates into night, there is almost no air to hold the heat, so the ground radiates its energy straight out to space and plunges below minus 180 degrees Celsius, around minus 290 degrees Fahrenheit. And because the orbit is so eccentric, the timing and intensity of these heating cycles depend on where Mercury is in its path. This is not an atmosphere-driven climate. It is raw orbital mechanics directly cooking and freezing bare rock. Now take that whole situation, the high speed, the strong gravity, the relativistic orbit twist, the extreme seasons without an atmosphere, and ask, What happens when you push those parameters even further on planets around other stars? When astronomers find rocky exoplanets that orbit their stars in just a couple of days, or even less than a day, they're looking at systems that are like Mercury turned up several levels. Those planets sit even closer to their stars, where gravity is stronger, orbital speeds are higher, and the effects of general relativity on their orbits are more pronounced. Their paths can precess faster, their temperatures can be much higher, and their surfaces, if they exist as solid surfaces at all, face levels of radiation and tidal stress that make Mercury's situation look mild by comparison. Some of these worlds may be partially molten on the surface, with atmospheres made of rock vapor. To make sense of those extreme exoplanets, scientists use Mercury as the training ground. If your models of orbit dynamics, relativity, and surface heating cannot reproduce what we see at Mercury, you cannot trust them when you apply them to a planet 3 times larger, 10 times closer to its star, and under much stronger gravitational and magnetic stresses. In that sense, Mercury is not just a local oddball, it's the basic template for star-hugging rocky planets across the galaxy. It tells you how fast they can move, how their orbits can twist, how their surfaces can bake and freeze, and where the limits might be before things fall apart. So now you've seen how Mercury's orbit is not just fast, but violent in a very technical sense, driven by extreme solar gravity and corrected by Einstein's spacetime. The next step is obvious. Under that kind of orbital stress, how does Mercury actually spin? What does a day even mean on a world where gravity, tides, and resonance all pull in different directions? On Mercury, the word day stops meaning what you think it means. If you tried to live there and keep time the way you do on Earth, your schedule would collapse almost immediately because the spin of the planet and its orbit around the sun are locked into a very strange pattern. Mercury rotates 3 times on its axis for every 2 orbits around the sun. That's a 3-to-2 spin-orbit resonance. In simpler terms, for every 2 Mercury years, you only get 1 full solar day, from one noon to the next. 1 Mercury year is about 88 Earth days, so half a year on Earth. So if you stand on Mercury and wait from one sunrise to the next, you're standing there for months. This is not a rounding error. This is a fundamental timing rule for the whole planet. From space, the math is clean. 3 spins, 2 orbits, locked in. From the ground, it feels completely off. Your calendar and your clock are no longer separate things. A day is 2 years, and a year is half a day. Sunrise is not a daily event. Sunrise is a season. The planet is rotating. The planet is orbiting, and the 2 motions line up in such a way that the sun crawls across the sky incredibly slowly. That's why any proper description of Mercury's time cycle always starts with this resonance. If you do not understand 3-to-2, nothing else about its day makes sense. So what does that do to the actual motion of the sun in the sky? Does it just rise slowly and set slowly? Or does something even stranger happen? Because of the way Mercury spins and moves around the sun, plus its stretched eccentric orbit, some longitudes get a sky show that looks broken. At certain locations, as Mercury approaches perihelion, when it is closest to the sun and moving fastest in its orbit, the sun rises over the horizon like normal, climbs, then does something that would look impossible to you. It slows down, stops, drifts backward for a while, stops again, and then continues forward. This is not poetic language. This is a real, predicted, and observed effect of orbital mechanics. Here's the basic reason. Mercury's rotation is turning the surface in one direction, carrying you eastward, while its orbital motion around the sun also changes the apparent position of the sun in the sky. Most of the time, rotation wins, and the sun moves steadily from east to west. But near perihelion, Mercury is moving along its orbit so fast that for a while, that motion cancels or even overpowers the effect of rotation. So the apparent motion of the sun stalls, then reverses. If you were standing at one of these special longitudes, you would see a double sunrise or double sunset. The sun would come up, pause, go back toward the horizon, and then climb again, or the reverse at sunset. That is one of the clearest signals that Mercury's spin and orbit are tightly coupled in a way that Earth simply never shows you. It is pure mechanics, no tricks, just the sum of rotation speed, orbital speed, and a non-circular path. This weird pattern raises a simple question. With such strong solar tides pulling on the planet, why isn't Mercury just tidally locked, always showing one face to the sun like the moon does to Earth? Based on basic tidal theory, that is exactly what you would expect. When a small body orbits close to a larger one, gravitational tides raise bulges in the smaller body. Those bulges feel a torque, a twisting force that over long periods slows the rotation until one side always faces the larger object. This is why the moon always shows us the same face. Early Mercury was spinning faster. Solar tides acted over billions of years, and they tried to pull Mercury into that same one-to-one lock, one rotation for one orbit. But there's an extra ingredient. Mercury's orbit is very eccentric, not a neat circle. That means the strength of the sun's gravity and the resulting tides change a lot over one orbit. When you plug that into the detailed equations of celestial mechanics, you find something important. For a planet with Mercury's spin rate and orbital shape, the 3-to-2 resonance is actually a more stable endpoint than a 1-to-1 lock. In other words, solar tides almost froze Mercury with one face toward the sun, but the eccentric orbit pushed the system into a different, more stable pattern, 3 spins every 2 orbits, and then it got stuck there. This is not guesswork. It comes straight out of modeling the tidal forces, the energy dissipation inside the planet, and the shape of the orbit. You do not need any special pleading or story. The physics naturally leads to almost tidally locked, but not quite. And that not quite is exactly the 3-to-2 state we observe today. Mercury sits in that equilibrium, and climbing out of it would require a huge external kick, which it is not getting. So now think about what this long, stretched-out day actually does to the surface. What happens to a piece of rock near the equator when sunlight lasts for months instead of hours? On Earth, most places get 6 to 12 hours of daylight in a normal day. The ground heats up, but then night comes. Air moves, clouds form, winds blow, heat gets shuffled around, and the surface cools. Mercury does not work like that. At the equator, once the sun rises, that spot can stay under sunlight for weeks to months. During that time, there is almost no atmosphere to block or scatter the incoming radiation, so the surface absorbs it directly, over and over, day after day, with no real break. Because the solar day is about 176 Earth days, you're talking about hundreds and hundreds of hours of continuous heating. The surface climbs toward around 430 degrees Celsius, about 800 degrees Fahrenheit. That is not just very hot, that is industrial furnace hot, hotter than the melting point of lead, which is around 327 degrees Celsius, about 621 degrees Fahrenheit. If you had a solid lead tool in your hand and dropped it on the ground at local noon, it would soften, sag, and deform over time. Not as science fiction-y effect, just basic materials behavior at that temperature. This is what happens when you combine 3 things: intense sunlight from being so close to the sun, an extremely long day, and no atmosphere. The sun beats down on the same patch of rock for weeks to months. Every photon that hits the ground either gets reflected or turned into heat. With almost no air to carry that heat away, the surface keeps climbing. On Earth, the hottest natural surfaces can touch or slightly exceed 70 degrees Celsius, around 160 degrees Fahrenheit, in extreme desert conditions. Mercury just leaves that in the dust. It runs all the way up into the 400 plus Celsius range and stays there for a long time. At those temperatures, you are way beyond uncomfortable. Plastics fail, many lubricants break down, a lot of common metals soften or lose strength. Even strong alloys expand so much that structures start to warp and flex. If you were somehow standing inside an armored suit on the surface with no active cooling, the suit would heat up from the outside in, and you would be cooked long before the sun ever set. The ground itself is radiating heat back up at you like a giant oven floor, all because the planet's slow rotation and tight orbit keep feeding energy into the same spots without a break. So the day side is worse than an oven, but you might think the night side is at least mild compared to that. It's not. What happens when the sun finally drops below the horizon and you step into the long Mercury night? On the night side, especially near the equator and mid-latitudes that were just roasting, temperatures plunge below minus 180 degrees Celsius, around minus 290 degrees Fahrenheit. That is colder than the average surface temperature on Pluto, a dwarf planet far out in the Kuiper Belt. You're getting outer solar system cold on the same world where the day side can soften metal. And this flip can happen over one extended day-night cycle. Once Mercury's surface is out of direct sunlight, there is almost nothing to slow the cooling. The hot ground radiates infrared energy straight into space, and with essentially no air to trap that radiation, the heat just escapes. On Earth, even a clear, dry night has some greenhouse effect from water vapor and other gases. On Mercury, it is basically open sky from rock to vacuum, so the ground temperature falls and falls until it matches the balance between what little heat leaks out from the interior and what is being lost to space. That balance point is brutally low. For any material left on the surface, this means it has to survive going from hundreds of degrees above zero down to almost 200 degrees below zero in Celsius over each full day-night cycle. Metals shrink, brittle materials develop micro cracks, different parts of any structure contract at slightly different rates, which build stress. Even rock is not immune. Repeated cycles like this over millions of years help open fractures, break down surface layers, and create a very hostile environment for anything that can't flex and recover. Why does Mercury swing this hard while Earth, at a comfortable distance from the sun, stays comparatively stable between day and night? The key difference is not just distance, it's the atmosphere, or the lack of one. Earth has a thick atmosphere that acts like a thermal blanket and a heat transport system. Sunlight heats the surface and the air above it. Warm air rises, cool air sinks, winds redistribute heat from hot regions to cooler ones. Oceans also store heat and release it slowly. On top of that, greenhouse gases trap some of the outgoing infrared radiation, so the planet doesn't lose heat too quickly at night. That's why most places on Earth don't go from oven to deep freeze in a single cycle. Mercury's atmosphere is an exosphere, which is basically a collection of individual atoms on ballistic paths, barely ever colliding. The pressure is around 1 trillion times lower than Earth's sea level pressure. That is so thin that for everyday purposes, you can call it vacuum. In that environment, there is no convection, no clouds, no real weather, no greenhouse effect. You just have direct solar radiation heating the ground when the sun is up, and direct infrared radiation from the ground to space when the sun is down. It's like running a planet in a thermal test chamber with the insulation removed. That's why the temperature pattern is so sharp, blazing hot where the sun is hitting, extremely cold where it isn't. No gentle gradients, no smooth mornings or evenings like you're used to. The physics is simple, the consequences are harsh, and it all comes back to that missing blanket of air. At this point, you might ask, if Venus is famously the hottest planet, how can Mercury claim to be more extreme in temperature? The answer is that the two planets are harsh in different ways. Venus has a thick, carbon dioxide-heavy atmosphere with clouds of sulfuric acid. Its surface temperature is around 465 degrees Celsius, about 870 degrees Fahrenheit. Almost everywhere, almost all the time. It's like a constant high-pressure oven. The atmosphere is so dense and the greenhouse effect so strong that night and day, equator and pole don't change things very much. The whole planet is locked into this uniform, crushing heat, which is terrible for anything trying to land there. But from a purely numbers point of view, the variation is relatively small. Mercury, by contrast, has a lower maximum temperature than Venus, roughly 430 degrees Celsius at peak, around 800 degrees Fahrenheit. But its extremeness isn't in the maximum, it's in the range. You go from about 430 degrees Celsius in the hottest daytime regions down to below minus 180 degrees Celsius at night. That is a swing of more than 600 degrees Celsius, over 1,000 degrees Fahrenheit. Earth's typical seasonal swings are on the order of tens of degrees Celsius, maybe 40 to 60 degrees between winter and summer in many locations. Mercury beats that by an order of magnitude regularly. So if you define harsh as always at a lethal constant setting, Venus wins. If you define extreme as how far the conditions swing between two states on the same world, Mercury is in its own category. It packages furnace-level day and deep space-level night in one cycle, and that is a different kind of problem, especially for engineering. And that brings up the practical question. What does this do to spacecraft? How do you design hardware that does not simply break apart when it sees those temperatures, plus intense sunlight, plus radiation all at once? Any probe going to Mercury has to survive not just one environment, but this whole range. Metals expand when heated and contract when cooled. If one part of a structure heats more than another, you get stress and bending. Most standard lubricants, the oils and greases used in moving parts on Earth, will evaporate, crack, or chemically break down at Mercury's dayside temperatures, or freeze solid on the night side. Electronics can overheat quickly if they absorb too much sunlight, or drift out of their safe operating range in the cold. So engineers have to control the thermal environment very actively. Missions like Messenger used large sunshades to keep the main body of the spacecraft in shadow, with the sun delivering up to 10 times the solar power per square meter that we get at Earth. Those shields were not optional, they were survival gear. The spacecraft followed carefully chosen orbits so that it did not spend too long directly over the hottest regions. Radiators dumped excess heat into space. Insulating materials slowed down how fast the inside of the spacecraft responded to the outside temperature. Moving parts and instruments were often tucked behind protective panels, so they never saw the full blast of sunlight. On top of that, designers had to think about what happens over years, not just days. Repeated thermal cycles can fatigue materials, so components were tested in vacuum chambers, run through heating and cooling sequences, and checked for cracks, warping, and performance drift. You're basically doing material science under alien conditions before you ever launch, because once you're in orbit around Mercury, you don't get a second chance. If something warps and jams when the spacecraft first faces peak temperatures, it stays jammed. When you combine that with the cliffs, basins, and global wrinkles carved into Mercury's crust, you start to see the bigger picture. This is a world where heat, cold, gravity, and time have all pushed the solid surface to its limits. So the obvious next step is to look at the scars, the giant impact basins, the planet-scale cliffs, and the way the whole globe has literally shrunk and crushed itself over billions of years. And the scars are still sharp. Start with the biggest wound, the Caloris Basin. This thing is about 1,550 kilometers across, roughly 960 miles. Roughly the distance between New York and Miami, but in one circular hole. That's not a crater you get from a casual hit. That's a basin you get when a huge asteroid or protoplanet slams into Mercury at tens of kilometers per second, dumps an insane amount of energy into the crust, and blows a hole deep into the lithosphere, the solid outer shell. That kind of impact doesn't just excavate a big bowl and stop, it sends seismic waves through the entire planet. Because Mercury's small and mostly metal inside, those waves can propagate right through the core and mantle, and they don't quietly fade out. When they reach the point on the opposite side of the planet, the antipode, they converge and interfere. That's where the shaking stacks up. When spacecraft mapped that antipodal point, they didn't see a normal crater field. They saw what scientists literally call weird terrain, a chaotic, jumbled region where the crust looks smashed, broken, and tilted in all directions, like the ground was shattered from below. That is the seismic echo of Caloris, frozen into the rock. It's one of the clearest examples we have of a single impact affecting an entire planet, not just the local area. So you've got this enormous basin and its opposite, weird terrain, showing you how hard Mercury was hit. But then you notice something else laid on top of the craters and plains. Long, sweeping cliffs that don't match what you see on Earth's continents. What are those? These are Mercury's lobate scarps, planet-scale cliffs that can be up to about a kilometer high, roughly 3,000 feet, and hundreds of kilometers long. Some run for more than 500 or 600 kilometers. They cut across older craters, older basins, older everything. They look like someone pushed large sections of crust together, forcing one block up over another. On Earth, big cliffs usually marked plate boundaries, subduction zones, or rifting regions, driven by moving plates and mantle convection. On Mercury, there are no shifting plates like that. These scarps are not the edges of plates, they are contraction features. The surface has buckled because the whole planet shrank. The outer shell had to wrinkle and break to adjust to a smaller interior volume. The dried apple analogy gets used a lot in textbooks, but here's the straightforward version. Mercury's interior cooled over time. Hot rock and metal contract as they lose heat. The inner parts of the planet slowly occupy less volume, but the rigid crust on top can't just smoothly slide down, so it has to compress. That compression is released by thrust faults, large slabs of crust being shoved over each other. And at the surface, those faults show up as these step-like cliffs, the lobate scarps. That raises a direct question. How much did Mercury actually shrink? Is this just a tiny adjustment or something you can measure in serious numbers? Models based on the observed scarps, combined with what we know about Mercury's interior, suggest its radius has shrunk by up to about 7 kilometers over billions of years. That's roughly 4 miles. Remember, that's not a local dent, that's the radius of the entire planet. If Earth suddenly did that, shrinking its radius by 7 kilometers, the crust would buckle, mountain ranges would pop up or collapse, coastlines would change, and global fault systems would light up. On Mercury, this happens slowly over geologic time, but the net effect is still dramatic. The old crust had to fold and fault to fit a smaller sphere. You can see the timing in the way the scarps cut across other features. Many of them slice through large impact craters and basins, which means the craters were there first. Then the planet continued cooling and shrinking, and the scarps formed later, plastered over the older impact record. You are literally seeing the planet change shape after the worst of the bombardment phase. Now, look at the craters themselves. Mercury's surface is packed with craters, from large multi-ring basins like Caloris down to small bowl-shaped pits only a few kilometers across. But what really matters is not just that there are craters, it's that they look old and stay that way. On Earth, plate tectonics recycles the crust, volcanoes resurface regions, erosion from wind, water, and ice move things out. A lot of ancient craters are erased. On Mercury, there is no plate tectonics, no rain, no rivers, no glaciers, and almost no atmosphere to drive erosion. Once a crater forms, it mostly just sits there, with only micrometeorite impacts and space weather slowly grinding it down over huge timescales. That means the surface still preserves craters from 3 to 4 billion years ago, when the solar system was going through its heavy bombardment phase. By counting how many craters of different sizes cover a region and comparing that to impact models, scientists can estimate how old that surface is. Densely cratered highlands are very old. Smoother plains with fewer large craters are younger volcanic or impact resurfaced areas. Mercury becomes a crater chronology chart you can walk on, each region telling you how intense the early impact environment was and how it changed over time. In that sense, mapping Mercury's craters is like reading tree rings, but much more violent. Small, fresh-looking craters sit on top of older ones. Large basins are overprinted by younger impacts and by the lobate scarps from global shrinkage. The order of events is written directly into the overlaps, if you know how to read them. So how does all of this compare to other battered worlds, like the Moon or Mars? Why isn't this just another cratered surface? The Moon is heavily cratered, with big impact basins and Maria, the dark lava plains that filled some of those basins. Mars is also covered in craters, especially in its southern highlands, with signs of ancient impacts, volcanoes, and some erosion from past water and wind. Both bodies give us a record of early solar system impacts, but Mercury adds an extra layer of violence, literally. On Mercury, you see high cratering levels like the Moon, but then you also see those huge contractional scarps draped across the crater fields, cutting through them, offsetting them. That combination tells you something important. Mercury didn't just get bombarded and then cool quietly. It was bombarded, then its interior kept evolving, cooling and shrinking enough to deform the entire crust after many of the big impacts had already happened. So Mercury's surface is not just an impact record, it's a mechanical record of a planet squeezing itself smaller, with giant basins marking external hits and global cliffs marking internal collapse. That dual history is more extreme than what we see on the Moon and Mars, which helps explain why planetary scientists keep coming back to Mercury as a key reference. If you want to understand how small rocky planets respond to both external violence and internal cooling, this is the case study. And under all of that, driving a lot of this behavior, is the thing you heard earlier but haven't fully explored yet. Mercury is mostly core, a huge metal interior wrapped in a thin, rocky shell. So the next step is obvious. If this world is basically a giant iron heart with a crust, what does that do to its gravity, its magnetic field, and its origin story? And how did it end up with a structure that breaks the normal recipe for rocky planets? You already know Mercury is small, but the numbers for what's inside it are way out of line with what a normal rocky planet should look like. Mercury's average density is about 5.43 grams per cubic centimeter. Earth's is about 5.51. Those numbers are almost the same, but Earth is much bigger, which means Earth's interior is squeezed harder by gravity, higher internal pressure. So it makes sense that Earth is denser. Mercury does not have that excuse. It's tiny, so by all normal logic, it should be noticeably less dense. And it isn't. The only clean way to explain that is to give Mercury an oversized metal core, mostly iron and nickel, taking up far more of its volume than Earth's core does. Models of its gravity and rotation say that core probably extends to around 85% of the planet's radius. Earth's core is closer to 50%. So Mercury is basically a giant iron ball with a thin rocky shell wrapped around it. Not a balanced mix of rock and metal, but a metal-heavy body with just enough silicate mantle and crust on top to count as a rocky planet at all. So you have to ask directly, how do you even build something like that in the first place? What went wrong or right in the early solar system to leave a planet that is mostly core? There are two main categories of explanation people take seriously, both of them extreme. One idea says that early Mercury started out more Earth-like, with a thicker rocky mantle and a more standard metal fraction. Then a giant impact hit it, not a small crater-forming collision, but a catastrophic event that blasted much of the outer rocky layers off into space. The lighter silicate material got stripped away, leaving behind a metal-rich remnant, the current Mercury. This is similar to what people think may have happened to create Earth's moon, but in Mercury's case, the result is a planet with its core exposed in a relative sense. The second idea focuses on the environment near the young sun. Early on, the inner solar system was filled with gas and dust, and the sun was much more active, throwing off strong radiation and intense solar wind. In that scenario, lighter materials closer in could have been eroded or blown away from the disk before they ever got built into full planets. That would bias the building blocks near the sun toward metal-heavier material, so any planet forming there would naturally end up with a higher metal fraction. Mercury would then be a survivor of a more aggressive inner region, not a victim of one giant collision. These are not just stories, they're grounded in physics and simulations, but right now, neither explanation wins outright, and you might end up needing a mix of both. Either way, the conclusion is the same. Mercury's structure is telling you that something very non-standard happened early on, while the planets were still assembling. This is a fossil from a violent, biased phase of planet formation, not a quiet, default outcome. If Mercury is mostly core, the next obvious question is that core dead and solid, or is it still active? Is there anything going on down there right now? The key clue is its magnetic field. It has a global magnetic field, not as strong as Earth's, but real and measurable, roughly 1% of Earth's field strength at the surface. That alone is a big deal. To get a global magnetic field like that, you usually need a dynamo, which means you need a conductive fluid, like liquid iron, moving and convecting inside the planet. Rotation plus that convecting fluid generate a magnetic field. If the core were completely solid and cold, you would not expect a strong global field. So Mercury, despite being small and old, still has at least part of its iron core in a molten or partially molten state, with enough motion to run a dynamo. That immediately tells you its interior is not static. There is still heat flow, still differentiation between solid and liquid layers, still energy being moved from the inside out. It's not as vigorous as Earth's system, but it's not dead. That's important because a long-lived core dynamo in such a small body adds another constraint to how it formed and how it cooled. How do we know the details of that interior, though? We can't just drill down and look, so where do the precise numbers come from? This is where gravity mapping comes in. When a spacecraft orbits a planet, its speed is constantly being nudged by tiny changes in the planet's gravitational pull. If the craft flies over a denser region, it speeds up slightly. Over a less dense region, it slows down slightly. These changes can be as small as millimeters per second, but with modern tracking using radio signals and Doppler shifts, mission teams can measure them. By collecting this data over many orbits, you can build a detailed map of how mass is distributed inside the planet. For Mercury, the MESSENGER mission did exactly this. By analyzing its trajectory, scientists inferred that the core is huge and dense. The mantle is much thinner than you'd expect for a planet of that size, and there's evidence for a lower density layer at the top of the core, likely rich in lighter elements like sulfur. Sulfur lowers the melting point of iron, which helps keep part of the core liquid for longer. Tying this back to the magnetic field, you get a consistent picture. A large iron core with some lighter elements mixed in, a thin overlying mantle, and a rigid crust that has been buckled by global shrinkage. So now step back and compare Mercury to the recipe you see in basic planet formation diagrams. Does it actually fit, or is it breaking the template? The standard picture for rocky planets is simple. You start with a mix of metal and rock, gravity pulls the heavy metal inward to form a core, lighter silicates form a mantle and crust, and you end up with a planet where metal is a minority by volume. Earth, Venus, and Mars all roughly follow this pattern. Their densities, radii, and internal structures are different, but they're all some balance of rock and metal that fits the textbook model. Mercury does not fit. It pushes that balance to an extreme. Core dominating, mantle reduced, crust thin, density too high for its size, and a still active dynamo running in a much smaller body than you'd naively expect. When astronomers now find exoplanets with very high densities for their size, worlds that seem too heavy to be normal rock and metal mixes, Mercury becomes the prototype. Those exoplanets might be scaled-up versions of the same idea, stripped cores of larger worlds, or planets that formed in metal-rich inner disks around their stars, just like the scenarios we consider for Mercury. In other words, Mercury forces you to expand the standard recipe. It tells you that rocky planets can end up being mostly core, under the right violent conditions, and that those objects can survive for billions of years with active interiors and magnetic fields. So when we look out at the galaxy and see dense, hot, close-in rocky exoplanets, Mercury is the warning label. It's saying some of these may not be normal planets with nice thick mantles. Some of these might be exposed metal hearts, forged and stripped by extreme early histories. And once you know Mercury has that giant, still active core surrounded by only a thin, rocky shell, another question becomes much more serious. How does that core interact with the brutal space environment so close to the sun? What does a magnetosphere look like when it's being hammered by intense solar wind at almost point-blank range? And how does a tiny, weak magnetic field even survive in that kind of constant attack? How does a tiny planet this close to the sun keep any kind of protective bubble at all? You'd expect the solar wind to just slam straight into bare rock with nothing in the way. But Mercury actually does have a magnetic shield. It's just small and constantly under threat. Because of that active iron core you heard about, Mercury generates a global magnetic field. It's weak compared to Earth's, only a few percent of Earth's surface field, roughly 1/20th if you look at certain measurements, but it's there, and that's enough to carve out a magnetosphere, a bubble in the solar wind where the charged particles are deflected around the planet instead of hitting it head-on. So even this small, scorched world has a miniature version of the same basic structure that protects you here on Earth. The size is very different though. On the day side, the point where the solar wind is stopped and pushed around, the nose of the magnetosphere, sits only a few planetary radii away from Mercury. There isn't much room. The boundary sits close to the surface compared to Earth's huge magnetic cavity. So the whole system feels tight and compact. Think of a small shield held right up to your body instead of a large one held far out. It works, but any increase in pressure from the outside is immediately felt all the way down. So what does that outside pressure actually look like this close to the sun, and how hard does it hit? At Mercury's orbit, the solar wind is both denser and faster than at Earth's distance. You're closer to the source, so the stream of charged particles, mostly electrons and protons, hasn't spread out as much, and it hasn't slowed down as much. If you think of the solar wind at Earth as a steady, medium-pressure flow, at Mercury, it's more like a high-pressure blast. The dynamic pressure, the effective push, is several times higher. That extra pressure constantly squeezes Mercury's magnetosphere. The dayside boundary gets rammed inward, the nightside tail gets stretched out, and the whole magnetic structure is being bent, twisted, and reshaped all the time. When the sun gets more active with stronger solar wind or coronal mass ejections, that compression gets worse. The small magnetosphere has very little slack, so it can be driven almost down to the planet's surface in some regions. For a weak field, that's a serious beating. And if the solar wind is hammering the magnetosphere like that all the time, does the field just quietly deflect it, or do things break and reconnect in more violent ways? Data from MESSENGER showed that Mercury's magnetosphere isn't calm at all. It's full of rapid, explosive events called flux transfer events, or FTEs. These happen when the sun's magnetic field, carried by the solar wind, hooks into Mercury's field and connects. Magnetic field lines that used to belong to the sun now link directly down to the planet, and vice versa. You get a short, intense channel where energetic particles can stream along those lines straight toward the surface. You can think of these as magnetic tornadoes, twisting tubes of field and plasma that grab particles from the solar wind and funnel them in. In those regions, the shielding effect of the magnetosphere is temporarily bypassed. Particles slam into the uppermost layers of rock and soil, and that impact knocks atoms out of the surface, a process called sputtering. Sodium, potassium, and other elements get kicked up into space, joining the thin exosphere that surrounds the planet. So on Earth, big space weather events give you bright auroras and satellite issues. What does space weather look like on a planet with almost no atmosphere, where all of this hits rock instead of air? On Earth, when charged particles spiral down magnetic field lines, they run into the upper atmosphere, excite atoms and molecules, and make them glow. That's the aurora. And the thick atmosphere absorbs a lot of their energy before they can reach the ground. On Mercury, there is no real atmosphere to light up. There is no real sky to burn. The same kinds of particles follow magnetic field lines, but when they come down, they hit the solid surface nearly directly. That means space weather on Mercury is mostly about erosion and chemistry, not light shows. Particle impacts chip atoms out of the crust, change the uppermost grains, and contribute to the exosphere. Over time, this constant bombardment helps darken and alter the regolith, the loose surface material. Micrometeorite impacts and thermal cycling do their part too. But the point is, the interaction between the magnetosphere and the solar wind goes almost straight into the ground. The energy that would normally be spread out in an atmosphere is focused into the top layer of rock. Every time the sun ramps up, Mercury's surface and exosphere respond quickly. The exosphere thickens and changes composition. Certain elements become more abundant. Then, as conditions calm down, those atoms escape, fall back, or redistribute. So if you study the exosphere in real time, you're effectively watching space weather play out with almost no buffer. It's a clean way to see how a star's wind strips at a rocky surface. And that brings you to the bigger point. This isn't just about one small planet. What does Mercury's battered little magnetosphere tell you about rocky planets that orbit even closer to their stars, in tighter orbits, under even stronger wind and radiation? Many of the rocky exoplanets we've found so far are closer to their stars than Mercury is to the Sun. Some orbit in just a few days, some in less than a day. If those planets have magnetic fields at all, their magnetospheres will be under constant heavy attack, even more than Mercury's. The stellar wind will be denser, the pressure higher, and the opportunities for reconnection events more frequent. It's not clear that a small, Earth-like field could keep a thick atmosphere safe in that environment for billions of years. Mercury gives you the lower end of that extreme regime, a small magnetosphere in a strong wind with direct evidence of reconnection, sputtering, and surface interaction. If your models of how magnetospheres behave under those conditions don't match Mercury, you can't trust them when you scale them up to super-Earths hugging their stars. In that way, Mercury is the template. It's the test case for star-skimming rocky worlds, showing you what happens when a planet is barely hanging on to its magnetic shield. And once you realize that the magnetosphere is constantly feeding atoms into space, you hit the next logical question. If there's no real atmosphere, just these ghost particles being knocked off and pushed around, what does air even mean on Mercury? What does an exosphere actually look like up close? And how can something that thin still tell you so much about the violence coming from the sun? You hear the word atmosphere and you think of air you can breathe, winds you can feel, clouds moving overhead, right? Mercury has none of that. It technically has an atmosphere, but it's so thin that for a human, it's the same as vacuum. On Mercury, what exists above the surface is an exosphere, not a normal atmosphere. In a real atmosphere like Earth's, molecules collide with each other all the time. They bounce, mix, carry sound, carry heat. You can feel wind as those collisions push on you. In an exosphere, the density is so low that atoms almost never hit each other. Instead, each atom follows its own ballistic path, like a tiny projectile. It launches off the surface, travels in a long arc under Mercury's gravity, and either falls back down, escapes to space, or gets knocked around again by radiation or particles. So what are those atoms actually made of? If you looked at Mercury through a spectroscope, what would you see floating above the rock? When astronomers point telescopes at Mercury and split its light into a spectrum, they see emission lines from specific elements. The strongest and easiest to detect are sodium and potassium. Sodium is the same element that gives streetlights their yellow glow. Potassium has its own distinct lines. On Mercury, both appear as bright signatures in the light scattered from the exosphere. Along with them, there are signals from oxygen, hydrogen, helium, and traces of other elements, all hovering above the surface in that super thin gas. These atoms are not part of some stable, permanent atmosphere. They're constantly being added and removed. Sodium and potassium can form a thin layer close to the surface. Oxygen and other atoms get released from minerals in the crust. Hydrogen and helium can come from the solar wind itself, implanting and bouncing back out. At any given time, the exosphere is more like a snapshot of ongoing processes than a static air layer. Its composition and density change with local time, latitude, and solar activity. So where do these atoms actually come from? What is physically knocking or lifting them off the surface into that exosphere in the first place? There are three main source processes, and all of them are active on Mercury. The first is sputtering. Energetic particles from the sun, mostly in the solar wind or tied to magnetic reconnection events, slam into the top few nanometers or micrometers of the surface. That impact is enough to knock atoms out of their positions in the solid and send them flying. Some of those ejected atoms reach escape speed and leave forever. Some fall back, some enter the exosphere for a while. Sodium and potassium are especially easy to sputter, so they show up clearly. The second source is micrometeorite impact vaporization. Space is full of tiny grains of dust and small rocks. When they hit Mercury at tens of kilometers per second, they release a burst of energy that melts and even vaporizes a tiny patch of the surface. This creates a hot, expanding cloud of gas and dust around the impact point. As that cloud expands, some atoms escape, some settle back down, but in the meantime, they contribute to the exosphere. This process goes on constantly. Thousands and thousands of tiny impacts per day over the whole planet.
The third source is thermal desorption, which is just a precise way of saying boiling off under heat. When the dayside surface reaches those 430 degrees Celsius, around 800 degrees Fahrenheit, some atoms have enough thermal energy to break their bonds with the surface and jump off. You don't get a boiling, churning atmosphere like a pot of water, because the density is too low and there's almost no gas above to trap them. But you do get a steady leak of atoms that simply evaporate into space at the hottest spots. Again, sodium is a major player here. All three processes are not only predicted in models, they're seen in the data. Changes in solar wind conditions correlate with changes in exosphere density. Micrometeorite flux models line up with background levels, and the dayside-nightside differences track with surface temperature. So this is not guesswork, it's a measured system. Now, here's the part that sounds like it belongs to a comet, not an inner rocky planet. If Mercury's exosphere is so thin, how does it end up with a tail that's longer than the planet itself? The key is radiation pressure from the sun. Photons from the sun carry momentum. When they hit atoms in the exosphere, especially sodium atoms that strongly interact with certain wavelengths of light, they can push those atoms away from the sun. Over time, enough sodium atoms get nudged in the anti-solar direction that they form a trailing tail stretched out behind Mercury along its orbit. This tail is not thick or bright like a comet's dust tail, but in the right wavelength, the sodium emission line, it stands out. Earth-based telescopes have actually imaged this sodium tail. They use filters tuned to that sodium line and see an extended structure stretching millions of kilometers, millions of miles behind Mercury. Its shape and brightness change with Mercury's position in its orbit and with solar activity. It's a direct, visible sign that radiation pressure and surface exosphere exchange are constantly at work. So even though Mercury looks like a bland gray dot in visible light, in sodium light it has this ghostly comet-like extension. So if the exosphere is constantly being stripped, reshaped, and replenished by impacts, heat, and solar particles, can we use it for anything, or is it just a side effect? This is where it turns into a tool. Because the exosphere responds quickly to changes in the solar wind and in Mercury's magnetic environment, it acts like a real-time meter for space weather near the sun. When the solar wind gets stronger or more variable, sputtering rates go up. When Mercury passes through different regions of the sun's magnetic field, the pattern of reconnection events changes, and that alters the flux of energetic particles hitting the surface. When local time shifts from night to day, thermal desorption ramps up. All of these effects show up as changes in exosphere density and composition. Spacecraft in orbit can sample the exosphere directly, counting atoms and ions, while telescopes from Earth can watch the sodium and other emissions over time. By combining those measurements with data on the solar wind and the sun's activity, scientists can back out how the near-sun environment is behaving. It's like putting a very sensitive, fragile detector right next to the star, except the detector is an entire planet that's constantly being sandblasted and heated. This is why Mercury matters far beyond our solar system diagrams. It's not just a dead rock with no real air. It's a live interaction zone between rock, ghost atoms, and stellar violence. And once you see that, the next question is even sharper. How can a planet this close to the sun, with this kind of exosphere and this kind of orbit, still hold on to cold, stable water ice at its poles? How do you put real, stable ice on a planet that can melt metal at the equator and keep it there for billions of years? That's the situation on Mercury, and the story starts with some very confusing radar data. Back in the 1990s, when astronomers bounced powerful radar signals off Mercury from Earth, they saw something that didn't fit the script. Near the poles, especially the North Pole, some regions came back unusually bright in radar. These radar bright patches looked a lot like what we see from icy surfaces on other bodies, like the icy moons of Jupiter. High reflectivity, strong, clean echoes. But this was Mercury, close to the sun, a place everyone assumed was totally dry. At first, the more comfortable explanation was rough or metallic terrain, because those can also give bright returns. Here's the twist, though. These bright patches were located inside craters that, based on Mercury's topography and the angle of sunlight, should be in permanent shadow, not just dark for a while, but dark forever. That's already weird, because you've got something very reflective sitting in places the sun never directly hits on a planet that is otherwise getting blasted with intense light and heat. The data kept saying this looks like ice, but common sense said no way. So the next question is obvious. How do you even get permanent shadow this close to the sun? Shouldn't the sun eventually shine into every crack and crater? The key is Mercury's axial tilt. Its spin axis is tilted by only about 0.03 degrees, compared to Earth's 23.5 degrees. In simple terms, Mercury is basically spinning upright relative to its orbit. There are no strong seasons the way we have them. The sun's angle in the sky at the poles barely changes over the entire Mercury year. Now, combine that with deep impact craters near the poles, the crater rims rise up, the floor sits down in a hole, and because the sun never climbs high in the sky there, its rays skim across the top but never reach down into the deepest parts. Those crater floors become what we call cold traps, places that literally never see direct sunlight. The temperatures down there stay below about minus 170 degrees Celsius, around minus 274 degrees Fahrenheit, almost all the time. At those temperatures, ice is stable. It doesn't sublime away quickly. It doesn't melt. It just sits, like ice in a freezer that never turns off. So now you can see how the geometry works. Mercury's tilt is so close to zero that deep polar craters turn into permanent darkness pockets, even though the rest of the planet is getting cooked. But seeing permanent shadow and seeing radar bright spots is still indirect. So the next step was clear. You needed a spacecraft up close to actually check what those bright patches are made of. Messenger, which orbited Mercury from 2011 to 2015, carried instruments that could do exactly that. One of them was a gamma-ray and neutron spectrometer. This kind of instrument doesn't take pictures. It measures high-energy radiation coming from the surface. Cosmic rays and solar particles hit the ground, interact with nuclei, and generate gamma rays and neutrons. The energy and number of those particles depend on what elements are in the top layer of the surface, especially hydrogen. When Messenger flew over those radar-bright polar regions, the spectrometers picked up strong signals consistent with hydrogen-rich material in and just below the surface. In other words, there was a lot of hydrogen there, and the most straightforward way to pack hydrogen into a cold, solid layer is as water ice. The data matched the idea of thick, relatively pure ice deposits covered by a thin layer of darker, insulating material, maybe a few decimeters to a meter thick. That dark cap keeps the ice extra cold by blocking what little scattered sunlight or thermal radiation might reach those spots. This is not a hand-wavy conclusion. It's direct compositional measurement, plus radar data, plus temperature modeling, all pointing in the same direction. The simplest explanation is that those bright patches in the polar craters are water ice, sitting in permanent darkness on the nearest planet to the sun. So then the next question hits you. Where does that water even come from? Mercury didn't form as a cold, icy world, so who delivered this material? And how did it get concentrated into those polar cold traps? The main supply chain runs through comets and certain types of asteroids, icy bodies from the outer solar system, or water-rich asteroids from farther out. Occasionally get nudged onto paths that take them close to the sun. Some of them slam into Mercury at high speed. When that happens, a lot of the ice and other volatiles in the impactor vaporize. Some escape immediately, but some stick around, forming a temporary atmosphere of water vapor and other gases. On a world like Mercury, with low gravity and high temperatures at the equator, most of that vapor will follow ballistic trajectories, hopping from surface to surface. As molecules move around, some inevitably find their way toward the poles, where the average temperatures are lower. And once a molecule of water hits a permanently shadowed, super cold surface, it can freeze and stay. Over millions to billions of years, many impacts and many migration cycles can slowly build up significant deposits in those cold traps. A similar process is thought to operate on the moon's poles as well. You can also add in some contribution from the solar wind, which carries hydrogen ions that can interact with oxygen in surface minerals to form hydroxyl and water. But the big picture is the same. You have a delivery mechanism, a way to move water around the surface, and a sink where it can't easily escape. The polar craters, once water lands there, it's effectively removed from the hot day, cold night cycle that dominates the rest of the planet. So now put the whole thing together and look at how extreme that system really is. What other planet gives you this kind of temperature split in such a small distance? On Mercury, you can start at the equator at local noon with surface temperatures around 430 degrees Celsius, about 800 degrees Fahrenheit, high enough to soften lead and stress most metals. Then you travel a few thousand kilometers toward a polar region, drop down into a shadowed crater, and you're standing on solid water ice, sitting at around minus 170 degrees Celsius or colder, about minus 274 degrees Fahrenheit. That's a temperature regime similar to deep space cryogenics. On the same world, within a relatively short distance, you have conditions like an industrial furnace and conditions like a permanent deep freeze. This is not a maybe or a one-time fluke. It's a stable, long-term arrangement. As long as Mercury's tilt stays essentially zero and the craters stay in shadow, the ice can survive, even while the rest of the planet cycles through brutal heating and cooling. That's why these deposits are so important scientifically. They're not just interesting because they're water, they're interesting because they show how powerful simple geometry and orbital mechanics can be. If you set the tilt and crater depth just right, you can park ice right next to a star. And once you accept that Mercury can hide ice in deep shadows while the equator is baking, you're ready for the next twist, because the surface is also doing something else that doesn't fit a naive burnt rock picture. It's richer in volatile elements than anyone expected for a world baked this hard. Volatiles are elements that normally don't like extreme heat, things like sulfur and potassium. In the old picture, the inner solar system was supposed to be stripped of those elements. The closer you are to the young, hot sun, the fewer volatiles you keep. So Mercury, the innermost planet, should have been the driest, most depleted of the rocky worlds. Instead, you see sulfur and potassium in amounts that do not fit that simple gradient. That one result already forced people to rethink the basic rule of inner equals baked, outer equals volatile rich. It means either the inner solar system was not as uniformly hot and stripping as we thought, or Mercury formed from material that had a very different history than the other inner planets. You're not looking at a uniform conveyor belt of increasingly scorched rocks as you move inward. You're looking at a patchwork where Mercury grabbed and kept stuff that on paper it should have lost. Then Messenger took it further by showing you something on the surface that looks completely out of place on an old, dead, airless world. It found hollows. Hollows are small, bright, shallow depressions on the surface, usually tens to a few hundred meters across, so roughly 30 to a few hundred feet. They tend to cluster inside impact craters, often on central peaks or crater walls, and they don't look like normal impact craters at all. They're rimless or have very low rims, irregular in shape, with sharp edges and very bright interiors compared to the darker background terrain. Those bright, crisp edges are a key clue. On a world that's billions of years old and constantly hit by micrometeorites, most surface features get softened and darkened over time. Hollows don't. They look geologically young, like they formed recently on top of older structures. In some cases, you can see them overprinting other crater features, which means they're younger than the crater they sit in. That alone tells you the surface is still changing chemically, not just being mechanically hit by impacts. So what is carving out these fresh pits if it's not new impacts? And why are they so closely tied to specific rock types and crater interiors? The leading explanation is volatile loss happening close to the surface. Certain minerals in Mercury's crust contain volatile elements, including sulfur and possibly other light components. Under the extreme conditions of Mercury's day side, those volatile-rich minerals can become unstable. They can break down and release gas directly into space, a process called sublimation if it goes from solid to gas, or more broadly, devolatilization. As those components leave, the material loses volume and structural strength. Over time, the layers just beneath the surface can weaken and collapse, leaving behind a shallow depression where material has disappeared or been eroded away. Because the newly exposed surfaces haven't been in space very long, they look bright and sharp. That's exactly what you see in the hollows. It's like the ground is slowly pitting and honeycombing itself where volatile, rich rocks are exposed. That means Mercury's surface is not frozen in time. It's still evolving right now, driven not by liquid water or atmosphere like on Earth, but by direct chemistry between heated rock and vacuum. Atoms are literally leaving the crust, atom by atom, under present-day conditions. The planet might be small and old, but it's not finished changing. Now go back to the sulfur story and connect it. Messenger's instruments measured sulfur in the crust at several weight% in some places. That is much higher than what you find in Earth's crust, and high compared to what you would expect if Mercury had formed in a strongly oxidizing, high-oxygen environment like Earth did. High sulfur content points to a chemically reduced environment during formation. That means less free oxygen and a different balance between metals, sulfur, and other elements when Mercury was being assembled. In a reduced environment, sulfur tends to bind with metals and stay in solid form even at high temperatures, instead of being lost as gas. So Mercury's crust and mantle end up with a composition that looks alien compared to Earth or Mars. More sulfur, different mineral types, and different melting and crystallization behavior. That also feeds back into how its core formed, how long it stayed molten, and how its volcanic history played out. You're not dealing with just hot basaltic lava and iron core, you're dealing with a planet built out of chemistry that leans in a different direction from the start. Put together, you have three big chemical signals shouting at you. Mercury has more volatiles than it should, it has fresh surface pits where volatile loss seems to be happening right now, and it has unusually high sulfur levels that point to a very different redox, oxygen versus other elements, balance during formation. Now, line that up with everything you already know: an oversized iron core, a thin mantle, a contracting crust that formed global scarps, ice and polar shadows, and a battered compact magnetosphere under heavy solar wind, and ask whether the standard textbook model for rocky planets still looks confident. The old model said something like this: close-in rocky planets form from refractory, non-volatile materials, mostly silicates and metals. Volatiles are rare that close to the star, so you get dense, dry worlds with normal core-to-mantle ratios and predictable crust compositions. Mercury breaks that at multiple levels. Its core is too big, its crust is too sulfur-rich, its surface is losing volatiles today, and its poles are holding onto water ice, all while being the closest planet to the Sun. Every time we added new data, we had to adjust the model, not Mercury. Mercury has stayed extreme. The theories have had to bend. In exoplanet terms, that matters a lot, because when we see dense, close-in rocky planets around other stars, we can't just say, oh, they're small Earths baked a bit more. Some of them might be Mercury-like, metal-rich, volatile-bearing, with strange surface chemistry and ongoing volatile loss. So Mercury isn't just an oddball you can ignore. It's a problem case that exposes the limits of our neat formation recipes. It's effectively saying, your simple story about inner rocky planets doesn't cover me. And if it doesn't cover Mercury, it probably doesn't cover a lot of extreme exoplanets either. And that brings up the next big question. If Mercury's chemistry is this strange, and its surface is this active chemically, what does its crater record really tell you about the early solar system? Can you still use its scars as a clean history of impacts? Or do you have to think of it as a time capsule that has recorded not just bombardment, but also billions of years of internal and chemical evolution layered together? When you look at Mercury's surface, you're basically staring straight into deep time, because almost nothing has come along to wipe the slate clean. The crust is acting like a physical clock for the violent early solar system. The way scientists turn that surface into a timeline is simple in principle, brutal in practice. You count craters, small ones, big ones, in different regions, and you compare those counts to models of how often objects of different sizes should have hit over the last 4 billion years. If one area is packed with overlapping craters of all sizes, it's old. It's been exposed to incoming rocks for a long time. If another area has far fewer large craters and mostly small, sharp ones, it's younger. It got resurfaced at some point, and then started collecting craters again. When you do that across Mercury, the result is clear. Most of the crust is ancient, older than about 3.5 billion years. Huge regions are heavily cratered, with big basins and dense fields of smaller impacts.
Only a minority of areas stand out as smoother plains with relatively fewer craters. Those smoother zones are younger, but still very old by Earth standards. You're talking billions of years, not millions. So the default state of Mercury's surface is early solar system fossil, not recently refreshed. That immediately ties Mercury to the idea of the late heavy bombardment, the proposed spike in impacts around 3.9 billion years ago, when the giant planets may have migrated and destabilized huge populations of asteroids. If that event really happened the way the models say, where would you expect to see the damage most clearly? Mercury sits deep in the sun's gravity well, closer than any other planet. When orbital resonances and planetary migration started tossing asteroids around, many of those destabilized bodies would have been flung onto paths that either hit the inner planets or the sun itself. Mercury is right in that firing lane, closer to the source of a lot of those new trajectories. So if there was a period when impact rates spiked, Mercury would have taken a lot of those hits, possibly more per unit area than Earth, simply because it's nearer the center. Crater statistics support the idea that Mercury's highlands and big basins record this violent era. Huge multi-ring basins, densely cratered terrains, and the overall age distribution all match the pattern of a world that got hammered early and then quieted down. You can't prove every detail of the late heavy bombardment story just from Mercury, but it absolutely looks like a witness that was standing right next to the shooting gallery when the system was most chaotic. Now look at those smoother plains you see around huge basins like Caloris. They don't have as many large craters as the surrounding highlands. They're flatter, more uniform, and spread out in sheets. So the question is, are those just areas buried by impact ejecta, or did something else happen after the crater formed? The best explanation, backed by crater counts and composition measurements, is that many of those smooth plains are volcanic, not just impact debris. After a massive impact like the one that created Caloris, the crust around the basin would be fractured and heated. That opens pathways for magma from the interior to rise. Over time, lava floods out, fills low areas, and cools into relatively smooth plains. Later impacts then punch into that lava surface, leaving a new, younger crater population on top. Messenger's instruments detected chemical signatures in some of these plains that match volcanic compositions, not just random mixed debris. And the way the craters are distributed in size and number fits the idea of a resurfacing event followed by a new round of impacts. That means Mercury wasn't just passively absorbing hits, it responded with internal activity, at least for a while, using impact-triggered volcanism to reshape parts of its surface after the worst of the bombardment in certain regions. On Earth, linking surface features to such ancient events is incredibly hard because our crust doesn't sit still. Plate tectonics constantly recycles it. Ocean crust sinks, continents collide, mountains rise and erode. The record of the first couple of billion years is mostly destroyed or deeply buried. You only get bits and pieces of that era in some very old rocks and zircons. Mercury has none of that recycling, no plate tectonics, no global system of moving plates, no ocean basins to subduct. That means once a big basin forms, it stays. Once a scarp cuts through the crust, it stays. Once a lava plain solidifies, it mostly stays. Aside from later impacts and slow space weathering, the surface is not being torn apart and remade every few 100 million years. So the break lines, scarps, basins, and plains you see are a mostly intact archive of early bombardment plus the planet's own internal cooling and contraction. That's what makes Mercury such a powerful time capsule. It doesn't just show you where it was hit, it shows you how it responded inside, and then it leaves the result out in the open for billions of years almost untouched. Compare that to other rocky bodies we use as historical records. The Moon gives you an excellent crater record, with big mare basalts doing some basins, so you get impact plus volcanic resurfacing. But the Moon doesn't show global contraction scarps on the scale Mercury does. Its internal evolution was different. It didn't shrink as dramatically. It doesn't have the same wrinkled globe look. Large asteroid Vesta gives you insight into basaltic crust and differentiated interiors, with giant impact basins and exposed layers. But it's much smaller and sits out in the asteroid belt, not deep in the sun's gravity well. On Earth, you get elements of both. You have the crater density and variety of the moon, you have volcanic plains that echo what we see on Vesta and other differentiated bodies, and on top of that, you have a unique global contraction history, with lobate scarps cutting across all that older terrain, all tied to a giant cooling core. It's like taking several different planetary case studies and compressing them into one world. So in one small ball of rock, you have a multi-billion-year data log, written in stone, telling you about the early impact environment, the timing of volcanic activity, the rate of interior cooling, and the mechanical response of the crust as the whole planet shrank. If you want a single object that encodes what did the inner solar system go through in its first couple of billion years, Mercury is one of the best candidates you have. And that brings you to a bigger, more precise frontier. Because Mercury doesn't just tell you about impacts and lava, it lets you test the actual laws of gravity themselves, down to fine details, by how its orbit shifts and how its mass is distributed. So the next step is to look at Mercury not just as a time capsule, but as a precision instrument, a natural experiment running right next to the Sun that we use to test general relativity and probe the structure of the Sun itself. You've seen Mercury as an extreme planet, but here's the part most people miss. This tiny scorched world is also one of the most precise scientific instruments we have for testing gravity itself. We don't just look at it, we use it. You already heard about Mercury's perihelion precision, the slow rotation of the closest point of its orbit around the Sun. Newtonian gravity plus the tugs from other planets explain almost all of it, but leave a small leftover. That leftover is exactly the part Einstein predicts. So you might think, okay, solved, move on. But scientists didn't stop there. They turned Mercury into a calibration tool. With radar ranging from Earth and tracking of spacecraft like Messenger, you can measure Mercury's position along its orbit to crazy precision. The timing of radar echoes and radio signals lets you pin down where Mercury is and how fast it's moving to within kilometers, then tens of meters, then better over many orbits. You can see tiny deviations from a simple Newtonian ellipse and check how well Einstein's equations fit. Right now, the match between general relativity and Mercury's motion is so tight that we're testing the theory down to parts per million in some parameters. If GR were even slightly off at solar system scales, Mercury's orbit is one of the places where that error would accumulate and show up. So Mercury isn't just an early victory from Einstein from 1915, it's an ongoing benchmark. Every new radar campaign, every mission tightens the screws on the theory. We're constantly asking, does reality still follow the math this closely? And so far, Mercury answers yes, with almost no wiggle room left. If we can measure gravity that precisely with Mercury, what else can we pull out of those orbital details besides GR works? Those tiny deviations in Mercury's orbit aren't only about relativity, they also hold information about the Sun itself, specifically about how round or slightly squashed it is. In physics language, we talk about the Sun's quadrupole moment. That just means if the Sun spins, it can bulge slightly at the equator and flatten a bit at the poles, like a very mild version of how Earth is wider at the equator than pole to pole. That tiny change in shape slightly changes how gravity works around the Sun, especially close in. So if the Sun were more squashed, Mercury's orbit would precess a little differently. By carefully separating out the relativistic part of the precession from anything caused by the Sun's shape, you can put limits on how big that equatorial bulge is. That directly feeds into models of how fast different layers of the Sun rotate, how mass is distributed inside, and how the solar interior behaves over time. In other words, by watching how Mercury moves, you're indirectly measuring properties of the Sun's deep interior that you can't see directly. You're using a planet as a gravity probe for the star it orbits. And we're not done, because the next generation of measurements is already underway, using a mission built specifically to push this even further. So what is Bepi-Colombo actually doing out there, beyond going to Mercury? Bepi-Colombo, a joint mission from ESA and JAXA, is not just a camera platform. It carries instruments designed to measure Mercury's gravity field, rotation, and orbital motion with extremely high precision.
By tracking the spacecraft's radio signals as it orbits Mercury, you can see tiny changes in its speed and position, just like with Messenger, but with better hardware, better clocks, and more focused experiments. From that data, you refine the map of Mercury's internal mass distribution. You tighten constraints on how its core and mantle are arranged. You measure how its spin axis wobbles over time. And you watch its orbit with enough accuracy to test not only general relativity, but also some alternative gravity theories that predict small departures from GR in strong fields near massive bodies. If any of those alternative theories were right, they might show up as slight mismatches in Mercury's orbit, or as anomalies in how its spin and gravity interact. So Bepi-Colombo is not just a Mercury mission, it's a stress test gravity mission, using Mercury as the test mass. But gravity doesn't just show up in orbits, it also affects the radio signals we use to track these spacecraft. So what happens to those signals when they pass close to the Sun on their way between Mercury and Earth? When a radio signal travels through curved space-time near a massive object like the Sun, general relativity says it should do two things. It should be delayed slightly, and it should be bent a tiny bit. The delay is called Shapiro delay. Instead of taking the simple straight-line travel time you'd calculate in flat space, the signal takes a bit longer because space-time near the Sun is curved. Paths are effectively stretched in a way that doesn't line up with simple Euclidean geometry. When we communicate with spacecraft near Mercury, their radio signals often pass relatively close to the Sun as seen from Earth. By measuring how long those signals take to go out and come back, and how their paths shift, we can directly test these predictions. You send a signal, you know when you sent it, you know when you got the reply, and you compare the timing to what general relativity says should happen. The match so far is extremely good, and every new mission tightens the error bars. So now you have Mercury doing double duty. Its orbit checks GR through perihelion precession, and the communication signals to and from spacecraft around it check GR through Shapiro delay and light bending. Same theory, tested in completely different ways with the same result. This is still accurate to ridiculous precision. And here's the big connection you might not think about at first. Why should tests around this small, hot planet matter for things as extreme as black holes and galaxy clusters? Because the same equations we use to describe Mercury's orbit and Shapiro delay are the core of how we calculate everything from stars orbiting the black hole at the center of the Milky Way to the way light bends around galaxy clusters to produce gravitational lensing, to how gravitational waves move through spacetime. Mercury is a small in size, but it's a clean, close, high-precision lab where we can push those equations hard and see if they crack. If general relativity was off by even a small amount in the solar system, those errors would propagate outwards, and a lot of our cosmology would be built on shaky ground. The fact that Mercury's orbit, Mercury's radio lengths, and Mercury's gravity field all line up with GR is one of the reasons we feel confident using the same math for systems that are millions or billions of times larger and more energetic. So this little inner planet, the one most people skip over, is quietly helping calibrate the rules of the universe. And once you see that, you can't just think of it as a rock. You have to think of it as a tool we're using to understand everything from the sun's interior to black holes. But there's still one more layer to the story of how the sun pushes and pulls on Mercury, and this one goes inside the planet again. Because that intense gravity doesn't just shape the orbit, it physically flexes the whole world, raising solid body tides, crushing the crust, and helping drive those global wrinkles you saw earlier. So the next step is to look at Mercury as a body being squeezed by the sun over and over for billions of years. You're used to hearing about tides as something that happens to water, but on Mercury, the thing that's rising and falling under the sun's pull is the rock itself. The entire planet is flexing. Think about this as clearly as possible. Every time Mercury goes around the sun's gravity raises a solid body tide in Mercury's crust and mantle. Not meters of ocean, but centimeters to maybe a few tens of centimeters of rock. It sounds small at first, a few centimeters up and down, but that rise and fall isn't just at one spot. It's spread over a whole planet. That means the entire crust is being slightly stretched and squeezed in a repeating pattern, orbit after orbit, year after year for billions of years. Rock is not perfectly rigid, but it's not liquid either, so when you flex it, you build stress. Some of that stress is elastic and snaps back. Some of it is permanent. Over time, that cyclic loading can help crack, fault, and fold the crust. So even though the tidal bulge height sounds modest, the integrated stress across Mercury's surface and interior is huge, especially close to the Sun, where the gravitational gradient, the difference in pull between the near and far side, is strong. So then the next thing you have to ask is, if the Sun is constantly flexing Mercury like this, and the planet is cooling and shrinking from the inside at the same time, what does that combination actually do to the crust over billions of years? You already know Mercury has those lobate scarps, long curved cliffs up to a kilometer high and hundreds of kilometers long. They're fault scarps, signs of thrust faults where one block of crust has been pushed up over another. The main driver is global contraction. As the huge iron core cools and solidifies, it takes up less volume. The outer shell has to adjust to a smaller interior, so it compresses and breaks. But those tidal bulges don't just sit quietly in the background. They add periodic stress pattern on top of the long-term contraction. Every orbit, certain regions are aligned with the Sun in ways that maximize tidal stresses. Other regions feel different patterns. Over millions and billions of cycles, that repeated flexing weakens some parts of the crust more than others. It encourages faults to nucleate along specific orientations. It helps existing weaknesses propagate and link up. You end up with those lobate scarps as not random wrinkles, but the long-term result of cooling plus tidal squeezing. The kilometer-high cliffs you see are the frozen expression of slow crushing under both internal and external forces. Now, if Mercury is being flexed like this, can we actually measure how much it squishes and use that to figure out what the inside is like, or is that too subtle to detect? Missions like Messenger and in future Bepi-Colombo can track Mercury's shape and gravity field with enough precision to see how it responds to tidal forces. As Mercury moves closer and farther away from the Sun along its eccentric orbit, the tidal force changes. The planet's shape and gravity field adjust slightly. Spacecraft orbiting Mercury feel those tiny changes in minuscule speed changes, measured via Doppler shifts in radio signals. From that data, scientists can extract what's called the love number, usually written as K2 for the tidal case. It's a single parameter that describes how deformable the planet is under a tidal field. A higher love number means the interior is more squishy, easier to deform. A lower number means it's stiffer and more rigid. That number is sensitive to the size and physical state of the core. If a large part of the core is liquid, the planet responds differently than if it were mostly solid. So by measuring the tidal response, you pin down how big the liquid part of the core is, how thick the mantle is, and how the density is layered inside. That's a big reason Mercury is so important. You're not guessing the interior from rough density alone. You're watching how the whole body flexes under the Sun's pull, and reading off internal structure from that flex. To see how different this is from what you're used to, it helps to line Mercury up against Earth and ask, where do tides really matter, water or rock? On Earth, you notice ocean tides first, meters of water rising and falling along coastlines, driven mainly by the moon and to a lesser extent by the sun. But the solid Earth also has tides. The rock deforms by a few centimeters, going up and down as the gravitational configuration changes. We can measure that with GPS and other geodetic tools, but most people don't feel it. The presence of oceans, atmosphere, and complex plate tectonics mixes and hides a lot of the clean, solid body response. Mercury strips all of that away. There are no oceans, no thick atmosphere, no moving plates. The thing that's flexing is the crust and mantle themselves, under direct solar tides with very little else in the way. That makes Mercury one of the cleanest solid tide experiments you can get for a planet around a star. You're effectively seeing this is what happens when you take a rocky body,
put it deep into a star's gravity well, and let it flex for billions of years without any oceans or plates to complicate the signal. Once you understand that, you can jump to the bigger question. If Mercury is the easy mode case for solid body tides around a star, what happens when you crank the tidal forces up by a factor of hundreds or thousands on planets hugging their stars much more tightly? Many close-in exoplanets around red dwarfs or sun-like stars orbit at distances much smaller than Mercury's. Some complete an orbit in a few days, some in less than a day. At those distances, tidal forces are enormously stronger. Instead of centimeters of solid body bulge, you can get kilometers of deformation. The planet can be forced into a permanent egg shape, with one side facing the star. Tidal heating inside the mantle can be intense enough to drive continuous volcanism, or even melt big parts of the interior. In extreme cases, the tidal stress can help tear a planet apart if it gets too close to the star's Roche limit. Mercury sits on the low end of that spectrum. It's close enough to feel strong tides, but far enough and small enough that it doesn't get ripped up. By studying how much Mercury flexes, how much it shrank, and how its surface responded, scientists get a baseline. They can scale that physics up to more extreme exoplanet systems and ask, at what point do these forces start dominating everything? At what point does a rocky planet stop being stable? Mercury is effectively the first rung on that ladder, the mildest form of solid tidal torture a planet can survive long-term. So by now, you've seen Mercury pulled, squeezed, and flexed by the sun in slow motion for billions of years, and you've seen how that plays into its surface, its interior, and its exoplanet analogs. The last piece of the picture is the hardest one for engineers. Under all of this gravity, heat, and radiation, why is actually getting a spacecraft into stable orbit around Mercury one of the most difficult tricks we've ever pulled off in planetary exploration? And what does that tell you about just how extreme this inner world really is as a target? Going to Mercury sounds simple. You're here, it's closer to the sun, just drop inward, right? That's not how orbital mechanics works, and this is where Mercury turns into a nightmare target for spacecraft. In orbit around the sun, Earth is already moving at about 30 kilometers per second, roughly 108,000 kilometers per hour, around 67,000 miles per hour. That sideways speed is what keeps us from falling straight into the sun. Mercury orbits closer in, moving even faster, about 47 kilometers per second. But to get your spacecraft from Earth's orbit down to Mercury's orbit, you don't just speed up toward the sun. You actually have to get rid of a huge chunk of your orbital energy relative to the sun. From low Earth orbit, you're tied to Earth 30 kilometers per second around the sun. To drop your orbit inward, you need to change your velocity so that, relative to the sun, you're no longer following Earth's wide path, but a much smaller one. That change in speed, the delta V, is enormous. If you try to do it with just rocket burns, you'd need absurd amounts of fuel, far more practical for a planetary mission. So falling toward the sun is, in practice, harder than going outward to Jupiter or Saturn. Lowering your orbit costs more than raising it. This is why every mission to Mercury looks like a crazy pinball trajectory, bouncing between planets, stealing and dumping orbital energy in small, careful steps. Instead of one clean burn, you're fighting the sun's gravity the whole way down, trying not to arrive going so fast that you just whip past Mercury and never come back. The first time we even managed to get a close look at Mercury was with Mariner 10 in the 1970s, and even that mission shows you how hard this target is to reach in any controlled way. Mariner 10 launched in 1973 and used a gravity assist at Venus to bend its path inward toward Mercury. That was a big deal at the time, the first mission to use one planet's gravity to reach another. But even with that trick, Mariner 10 didn't have enough fuel and control authority to slow down and stop at Mercury. It could only do flybys. It flew past Mercury 3 times between 1974 and 1975. Those flybys were still revolutionary. Mariner 10 imaged about 45% of the surface, giving us our first detailed look at the cratered terrain, the Caloris Basin, and some of the big scarps. But more than half the planet stayed in darkness or poor viewing geometry. There was no global map, no long-term measurement of the magnetic field, no gravity mapping. The mission's trajectory was limited by what was possible with one Venus flyby and the rocket technology of the time.
It proved we could get there, but not that we could stay. Decades later, Messenger was the first mission to actually orbit Mercury, and its path to get there explains very clearly how extreme the energy problem is. Messenger launched in 2004, and it did not just burn straight for Mercury. It did one flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury itself before it finally slowed enough to be captured into orbit in 2011. That's 6.5 years of careful gravity assists, each one shaving a bit of heliocentric velocity, each one bending the trajectory closer to Mercury's orbital speed and distance. Every flyby is a chance to trade some of the spacecraft's orbital energy for a change in path, without burning huge amounts of fuel. Earth and Venus essentially do some of the braking for you. By the time Messenger did its Mercury flybys, it had already lost a lot of its original orbital energy around the Sun, but not enough to just slam on the rockets and stop. It needed those passes by Mercury itself to bleed off even more. Only after all that did it perform a major burn to get into an extremely elliptical orbit around the planet. That whole sequence is the practical answer to why don't we just go there? We can't afford the delta V to drop straight in, so we take the long way around, using the planets as speed brakes. Bepi-Colombo, the current joint ESA-JAXA mission, pushes this even further, making it very clear that Mercury orbit is one of the hardest kinds of orbits to achieve in the inner solar system. Bepi-Colombo launched in 2018, and its cruise profile includes 1 Earth flyby, 2 Venus flybys, and 6 Mercury flybys before it can go into orbit. That's 9 flybys in total, spread over several years, each one carefully timed to adjust the trajectory and reduce the spacecraft's energy relative to the Sun. In terms of simple distance traveled, Bepi-Colombo will cover billions of kilometers, looping around the inner solar system just to end up a bit closer to the Sun than Earth is. That sounds crazy until you remember the core problem. You're not trying to move a long distance. You're trying to change speed and orbital size in a very precise way, without carrying a fuel tank so big it makes the mission impossible. Every pass past Venus and Mercury is a controlled exchange of energy that replaces the burn you'd otherwise need to do with the engines. And of course, even if you solve the orbital mechanics and finally get into orbit at Mercury, the environment waiting for you is a whole new set of engineering problems, because the Sun is now much stronger in every sense. At Mercury's distance, the solar flux, the power from sunlight hitting each square meter, can be up to about 10 times what you get near Earth. That's on the order of up to 14 kilowatts per square meter in certain mission phases. If you think in household terms, that's more power than 10 strong electric kettles or several large space heaters hitting every square meter of any unprotected surface constantly, plus the planet itself radiating heat back at you when you pass over the dayside. To survive that, spacecraft near Mercury need aggressive thermal control, large sunshades to keep the main bus in permanent shadow, highly reflective insulation to bounce as much sunlight as possible, and radiators placed carefully so they can dump excess heat into space without reabsorbing too much from the planet or the Sun. You can't just cover the craft in solar panels and call it a day, because too much absorbed energy will cook the instruments and electronics. Orbit design becomes a thermal problem as much as a science one. Messenger used a very elliptical orbit, bringing it close to the surface for short periods, then letting it swing far out where it could cool down and see less intense radiation. The timing of observations and maneuvers is wrapped around the need to avoid overheating. Bepi-Colombo uses a complex configuration of 2 science orbiters and a transfer module, with dedicated shields and orientations to keep the sensitive parts alive as it spirals in. Lubricants have to be chosen that don't outgas or break down at high temperatures. Structures have to handle expansion and contraction from repeated passes over hot and cooler regions. Sensors have to cope with glare and scattered light from the Sun, plus strong ultraviolet and X-ray flux. Every part of the mission is a fight against an environment that is trying to cook the spacecraft from all directions. So when you put all of this together, the orbital energy you have to lose to drop from Earth's path to Mercury's, the years of gravity assist needed to avoid carrying impossible amounts of fuel, and the brutal thermal and radiation conditions in close solar orbit, you see why we've sent far fewer missions to Mercury than to Mars or Jupiter. This is not an easy target. This is one of the hardest tricks in spaceflight, and yet we keep doing it. Because Mercury isn't just an oddball planet, it's the local blueprint for extreme worlds everywhere. Once you fought your way down into its orbit, survived its heat, and mapped its interior and space environment, you're holding the key to understanding a whole class of exoplanets that live even closer to their stars, in places where extreme stops being a label and becomes the default setting. You'd think Mercury is a one-off freak, a local glitch in the solar system, but once we started finding planets around other stars, the opposite turned out to be true. Mercury is actually the warning label, not the exception. Out there, we see rocky exoplanets that are bigger than Earth, orbiting their stars in less than a day. Some complete an orbit in 10, 12, 18 hours. Take everything you now know about Mercury, the metal-rich interior, the high density, the close-in orbit, the brutal radiation, and then crank the gravity and temperature up another level. That's what super-Mercuries and ultra-short-period planets look like. A lot of them sit so close to their stars that the stellar disk would take up a huge chunk of the sky, and their surfaces, if they're solid at all, are probably at lava ocean temperatures. If we didn't have Mercury as a reference, these systems would feel completely alien. The idea of a dense, close-in rocky planet with a giant core and a weird orbit would just be pure speculation. Instead, we can point at our own innermost planet and say, we've seen this pattern before, just at lower intensity. Mercury gives you a starting template: dense, core-dominated, baked by radiation with a warped orbit and a tortured day. The exoplanets just take that template and scale it up. So then you hit the deeper question. How do some of these exoplanets get so dense, so metal-heavy, that they barely look like planets anymore? And why does Mercury keep showing up as a small-scale version of that story? One idea that fits both Mercury and some of these exoplanets is stripped cores. Start with a bigger planet, with a normal mix of rock and metal, then hit it with something big, or park it too close to its star for too long. A giant impact can blast away outer layers, leaving a metal-rich heart behind. Intense stellar radiation and wind can also erode away the lighter, thinner mantle and any atmosphere, especially over hundreds of millions or billions of years. In both cases, what you're left with is a remnant mostly core by volume. When we measure exoplanets that are smaller than Neptune but much denser than Earth, some of them come out with densities that are hard to explain with normal rock plus metal mixtures. Mercury gives you a concrete example of how you can get there: a huge iron core, thin rocky shell, extreme proximity to the star, violent early history. You don't have to guess that stripped cores exist. You already have one in your backyard. On a much smaller scale, it's the same basic physics, just done at different energies and distances. Now push the system even harder. What happens when a planet orbits so close to its star that Mercury's already intense tidal and magnetic environment looks tame by comparison? Mercury already gets solid body tides and rock, a magnetosphere being squeezed and reconnected, and an exosphere being stripped by solar wind. But its orbital period is 88 Earth days, and its distance from the Sun is still large compared to a lot of ultra-short period exoplanets. Some of those worlds sit only a few stellar radii above the star's surface. They complete orbits in hours, not months. The tidal forces there can be thousands of times stronger than what Mercury feels. The planet gets pulled toward an egg shape. Interiors can be heated continuously by tidal flexing, keeping mantles partially molten, and surface conditions can be a constant storm of charged particles and extreme radiation. Magnetic interactions ramp up. A close-in planet with a magnetic field could be directly connected to the star's magnetic field in a strong and persistent way, driving currents and energy transfer that we barely see in the Mercury-Sun system. The stellar wind is denser, faster, more destructive, and any atmosphere that tries to form can get stripped incredibly fast. The environment Mercury lives in is already harsh, but for these ultra-sun-skimming planets, it's the mild end of the same physics, same equations, bigger inputs, more violent outcomes. So when you talk about habitable zones around stars, regions where liquid water could exist on a surface, how does Mercury help define what absolutely does not qualify? No matter how optimistic you are, Mercury is the hard proof that being close to a star does not mean warm and cozy. It means exposed. At Mercury, you have temperatures swinging from about minus 180 degrees Celsius, around minus 290 degrees Fahrenheit, up to about 430 degrees Celsius, around 8
800 degrees Fahrenheit. You have almost no atmosphere, just a thin exosphere of ghost atoms. You have intense solar radiation, strong UV and X-ray, constant solar wind bombardment, and violent temperature cycles that stress any material you put there. So when scientists draw the inner edge of the habitable zone around a sun-like star, Mercury sits well inside the absolutely not region. It's the anchor for what too close really looks like. If a planet orbits closer than Mercury, or gets more flux than Mercury does, you're not in some marginally warm beach zone. You're in a place where surfaces can melt, atmospheres can be stripped, and chemistry is dominated by extreme heat and radiation. Mercury sets that boundary in a concrete way, not as a theory, but as a real world you can study from orbit. Now step back and look at what spending this much time with Mercury has actually done to your mental model of planets. Has it just filled in a trivia slot, or has it quietly rewired what you think rocky planet means at the extreme end?
By the time you've gone through Mercury's orbit, you've dealt with high orbital speed, eccentric paths, and relativistic precession. By the time you've gone through its day, you've seen 3 to 2 spin orbit residents and double sunrises. By the time you've looked at its temperatures, you've seen a single surface jump from cryogenic cold to metal softening heat. You've walked across Caloris Basin and global scarps, learned that the crust shrank as the core cooled, and seen how impact history and internal evolution are written in overlapping scars. Then you added the giant iron core, the still running dynamo, the fragile magnetosphere that's barely holding off a strong solar wind, the ghost thin exosphere with its sodium tail, the water ice trapped in polar shadows, the volatile rich crust with fresh hollows forming as materials sublimate away, the crater chronology that records the early solar system, the gravity tests that lock down general relativity, and the tidal flexing that turns the whole planet into a long-term stress test for rocky interiors. Put all of that together and Mercury stops being the small one next to the sun. It becomes the upper limit case for rocky planets that aren't being torn apart. It's the benchmark we use when we look at extreme exoplanets and ask, is this just like Mercury but more, or does this go beyond even that? Every time we see a dense, hot, close-in world, we're basically asking, how far from Mercury is this in composition, in orbit, in stress? So this small gray sphere, orbiting at high speed in a blast furnace of radiation, ends up setting the scale for what extreme really means for solid planets, not just here, but across the galaxy. Once you understand Mercury properly, those super hot, metal-heavy, star-skimming exoplanets stop looking impossible and start looking like the logical next step on a spectrum that begins right at the inner edge of our own solar system. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.